I'm Phil Salmony, a technical consultant for Altium, and in this video I'd like to go through some common beginner PCB design mistakes and how to remedy them. I'll show you some guidelines for layout and routing, and that'll really help you improve your PCB designs. I do a fair amount of design reviews for PCB design engineers, and these are issues I come across quite frequently. These issues can be harmful for signal integrity, EMI, and so forth, so it's really good that we tackle them in this video. If you'd like to give Altium Designer a try for yourself, please check out the link in the description to get a free trial of Altium Designer. Without further ado, let's get started. The most common PCB design mistake I see that novice PCB designers make is that of trace spacing, and to me this is one of the most important aspects. Normally from a manufacturer's website or when contacting your manufacturer, they'll let you know what their manufacturing capabilities are. So what are the minimum clearances they can produce, trace spacing, track to pad, to through holes to vias, and so forth. And this information you would then enter into Altium Designer, going to design, rules, and you'd import all of your information from your manufacturer. And this sets up your minimum clearances and trace widths and so on. Now this is all fine and good, and usually this is the first step a PCB designer should usually do with the initial board design. But then once this has been imported, that doesn't mean you should stick to the minimum clearances and trace widths possible. For example, this design here, this is a microcontroller with a lot of these pins needed to be routed out. This might be ADC channels, next digital channels, and so on. What I often see is this kind of pattern. Immediately coming out of the irrelevant IC, the PCB designer has chosen just to simply use the minimum clearance and route all of these traces next to each other. This is bad for several reasons. First of all, this is right at the edge of the manufacturer's capabilities, so things could go wrong if we're right at the manufacturer's capabilities. Means we might get a lower PCB yield, but more importantly, because of these really narrow spacings between these traces, we're going to get cross-coupling between these signals. So a signal maybe apparent at ADC input 5 will couple over quite strongly depending on the length of these parallel segments and the rise time of these signals. ADC in 1.5 will couple in over to ADC in 1.6 and vice versa, simply because we are not keeping enough clearance between these traces. Let me show you a better way of routing these traces. We have the space, so let's use it. I would like to route out the pad and immediately go as far away as I can within reason, of course taking account decoupling capacitors and so on, and give myself as much clearance as possible from all these other traces, for example like so. Compare this to the situation before. We've increased our spacing considerably, and this will minimize our crosstalk. A good rule of thumb is to keep a minimum spacing or clearance between traces of 3 times the dielectric thickness. If we go to Design Layer Stack Manager, we can see the board stack up. So layer 1 signal to ground, we have a dielectric in between of 0.1 millimeters. So this rule means keep at least 3 times the dielectric thickness spacing between traces, which is 0.3 millimeters in this specific example. So for example, this trace on the left here has a clearance of 0.6 millimeters, so we're well above 0.3 millimeters. Now there might be situations where you can't keep this spacing. It will be inevitable in some PCB designs, but the important thing is that if you have the space, you should use it. Also try to keep the parallel segments between traces as short as possible. Another common beginner PCB design mistake is to use the same trace width for any type of trace. So be this an ADC trace, a high impedance node, a high speed signal trace, or power trace. It might seem convenient to just use the same trace width for everything, but it certainly isn't optimal. For example, if we look at this ADC input trace over here, this will be high impedance. For a high impedance trace, which is very sensitive to noise, I want to minimize any coupling to this. The way I can do that is by reducing my trace width. So if I route out of this, I don't want to use, for example, a 0.5 millimeter trace. I want to use something quite considerably smaller. It can't, of course, be generalized to what trace width you should always be using, but 0.5 millimeters is a very broad, thick trace. So I might use something, for example, 0.2 millimeters. Remember, you should stay within your manufacturing capabilities and far away from any extremes. Compare that to, for example, routing this 3.3 volt trace. 3.3 volt trace, I don't want to route, for example, at 0.1 millimeters or 0.2 millimeters. Typically, power traces will carry more current than a signal trace. And then again, this depends on the example. Sometimes you might even want to use whole planes to carry power. In this case, this is simply to feed some sort of external circuitry, maybe a couple milliamps. With a trace width of 0.5 millimeters, for example, as I'm routing out here, you can actually carry quite a considerable amount of current. To see what current a trace can carry, I highly recommend the Saturn PCB Design PCB Toolkit. If you go to the Conductor Properties tab, we can type in a conductor width, PCB thickness, copper weights, and so on. You can leave most of this as default, but we can vary the conductor width. So if I type in 0.5 millimeters, as in our example, and click Solve on the bottom right, you can see the conductor current, the maximum, is over 1.5 amps for such a fairly small trace. So we shouldn't overdo the size or the width of a conductor traces. We should always optimize for the situation we're in. Even if we go down to a 0.2 millimeter trace and click Solve, this can carry almost an amp, which is quite surprising to most people. We can also, of course, see the voltage drop over a certain distance, power dissipated, and so forth. So remember to vary your trace width depending on what signal or power you're routing. A special case, of course, needs to be made for controlled impedance traces, but this is not in the scope of this video. As with trace width, we can also look at via sizes and dimensions. For vias, we have a few more parameters that we can play with. In this example, we'll just be looking at simple through-hole vias, so nothing fancy such as buried or blind vias and so on. You can see a couple of example vias on the screen at the moment. We might have typical vias. We look at the top one that has a 0.9 meter diameter, so this is the entire via diameter, with a hole size of 0.5 millimeters. If we take the diameter, 0.9 millimeters, subtract the hole size, 0.5 millimeters, and divide that by 2, we get the size of the annular ring. So 0.9 minus 0.5 over 2 is 0.2 millimeters. So the width of this ring here is 0.2 millimeters. And this is oftentimes a very determining factor for the manufacturer or the manufacturer's capabilities. Typically, you want an annular ring of around 0.15 millimeters. Of course, there are times where you need a smaller annular ring for very dense designs, fine pitch BGAs, and so on. But as a rule of thumb, you want at least 0.15 millimeters annular ring. The hole and pad size also will vary depending on what requirements you have. For example, a thicker board will typically require a larger drill size to be manufacturable. My go-to vias are 0.7 millimeter diameter and 0.3 millimeter drill. If I require a smaller via, for example, this might be very small, I go with 0.5 millimeters pad and 0.2 millimeters hole. Of course, the size of my via determines also the current carrying capabilities. Again, as a demo using the Saturn PCB Design Toolkit, I can type in via hole diameter, pad diameters, and so on. If I just take the default with a 0.25 millimeter via hole and a 0.5 millimeter pad and click Solve, you can see the via current is about 2 amps. And this is a pretty good rule of thumb. A normal sized via will be able to handle about 1 to 2 amps of current. So if you're routing, for example, a power supply, you can use that as a rule of thumb to how many vias you need to be able to supply this amount of power or current. In beginner PCB designs, I often see annular rings like the via you see over here. So a very large drill and comparatively a very small pad, and we get this very, very thin annular ring. And this is something you should definitely avoid. So if you're unsure, stick to one of these default via sizes, 0.7 millimeter pad, 0.3 millimeter drill, as you get more comfortable to knowing what via size is right for you. Another very important and incredibly overlooked aspect when starting out with PCB design is placement, and in particular, proper placement of decoupling capacitors. Because of the nature of power distribution networks, we're going to have resistances, inductances in path or in series of our power distribution network, which can lead to severe voltage drops at ICs if they suddenly require large gulps of current. The way we can mitigate that is by placing local energy storages directly at the IC pins, and with focus being on pretty much directly at the IC pins. For example, this microcontroller in this picture, this is a QFP package, has power and ground pins, for example, 18, 19. If I grab my decoupling capacitor, which also has the same pins, so ground and power, a lot of times you will see beginners place the decoupling capacitors far out with very thin traces, for example, like this. And this is as far away as what you should be doing as you can be. What we want is our local energy storage to be as close as reasonable to the pins, for example, like this, making sure we can still route out from the remainder of the package. And this can, of course, become quite difficult, and it becomes a challenge as of what to prioritize. Typically, for low-speed designs, you will have routed power and a dedicated, or at least one dedicated ground plane directly below the IC. This way, you can drop a via below and then route power. If you then also have a dedicated power plane, in this example maybe a 3.3 volt plane, we can place vias between the components power and ground pins and between this decoupling capacitor, so we also get the benefit of the capacitance of the plane. For example, you might see a structure like this, which is actually a great method of decoupling or bypassing these IC pins, and we still have to route out the tracks. We have ground and power pins, closely spaced vias, within reason of course for manufacturability, which go to the internal power and ground planes, and then this decoupling capacitor close to the relevant IC pins. If you measure, we simply have a very small distance of about 2 mm between the relevant pads. Keep in mind, I've also tried to keep clearance between the vias and any other non-related pads. Then I can simply route out with a trace that's as wide as the IC pad into the via on both sides, and then use thick traces from the decoupling capacitor pads into the vias. For example, like so. To have closely spaced vias, this minimizes inductance. We've placed our decoupling capacitor very close to the IC pins, but still given us space to route out the relevant microcontroller pins. The final tip I'd like to give you is using solid reference planes directly adjacent to any signal layer, as well as directly adjacent to any power planes you might have. Oftentimes in more complicated PCB designs and multi-layer stack-ups, you'll have more than one ground plane. Here are also some tips and some beginner mistakes I often see that you should avoid. In this example, I have a solid ground plane on layer 2 and on layer 3. On layer 1, I then might have signals. You always want to keep any signal trace running adjacent to a reference plane. This is ground typically, but can also in certain cases be a power plane. So remember to route signals and power over a reference plane. In certain cases, of course, you might have to route your signal traces close to vias of different tracks or not ground vias. You can see as I move this power via, for example, around, below in Altium, I can see the ground plane has been voided. Of course, I have to keep some clearance between different net vias, pads, planes, and so on. If I have a really close power via, my track is actually running over a tiny bit of a void of the ground plane underneath. My ground plane underneath has been cut because of this via. So a better way now to route this trace to make sure I have a solid ground plane underneath is, for example, like so. Not only do I want to have my ground plane directly underneath, I also want to have space underneath that is still filled with ground. For example, like this satisfies the requirement that we need to have a ground plane directly below the trace, but it doesn't satisfy the requirement that we need to have a ground reference either side as well. This is because we have fields between the signal trace and the ground plane below, and the fields don't just appear directly below the trace, but they spread out. So thank you very much for watching this video. I hope these PCB design tips were useful, and you can incorporate them into your next PCB designs, or even improve some old PCB designs of yours. Thank you for watching, and I hope to see you in the next video. Bye bye.